So we are running up on lunchtime, and I want to make sure Jupiter has time to give his talk. So again, this hackathon schedule was sent out this morning by email. We'll send it out again um, this evening after we're finished with the workshop for the day. Um, and then we'll go over this in more detail tomorrow. Again, have some links here. This slide deck is in the folder if you need to check these links. We do have this hackathon interest survey. Please do fill that out. Um, when you get a chance today. Sorry, just to let us know if you're intending on participating in the hackathon. I'll put these links in the chat while Jupiter's getting set up as well. Please do post your ideas to the Slack channel. And if you would like to give a lightning talk, please go ahead and sign up with this link, which again, I'll drop in the chat in just a minute. So if you'd like to do a lightning talk tomorrow or Sunday, go ahead and sign up. And then we'll have a couple of sessions next week, which we're still working on getting scheduled for people to come give lightning talks. If you'd like to give your talk again during one of those sessions, that's fine as well. So I think with that, I'll go ahead and turn things over to you, Jupiter.
All right, let me just set things up here. Okay, are you guys able to see my slides? Yep, cool. So I will be talking a little bit of an idea that I had over the past few days. It also involves some of the aspects that I myself, like the reasons why I'm here in this workshop and what I want to do with CompuCell. This is going to be relating to cellular protrusions. So I, again, made some very few slides here with some ideas to toss it out here. In the math bio department that I belong to, we say that this video is way overplayed. But it's it's basically impossible to talk about cellular protrusion without showing this video. I tried my best to find better videos, but this one is always the best. But not only videos like this I have access to, but I also work directly with a lab of Dr. Oran Winner in San Francisco. And he has a lot of data on, so this right now is data from a microscope, already processed in Python and everything. There's several things that we can talk about this data here that I'm presenting on the screen. But I'm mainly interested on is to make a cell that somewhat behaves like that. In the video here, it kind of plays too fast, but there's these circles. These circles show optogenetic stimulus. So basically, they shine light on a cell, and the cell kind of wants to go towards the light. I joke that it becomes like a little fly. It likes to chase light. Suddenly, it stops chasing bacteria and it starts chasing light. Um, and again, it's nice that we had a conversation about networks today. It's a very complex network that governs from the stimulus of the optogenetics all the way to the cellular protrusion. But what I mainly focus on, and especially my research, is just really that very last part there, where we have some input. There are some proteins that bind to the cellular membrane. It pulls the cellular membrane towards whatever the stimulus is coming from spatially, basically helping the cell to chase a stimulation. This is given by, again, I'm super glad this conversation networks happened today. This is given by one of the formulations that I use that is called the wave pinning. On the right, I have the ODEs for it, but I feel like the network here represents really well what happens. You have somewhat a protein. Here I'm calling it REC. We usually say, especially for protrusions, the protein that causes this is REC, but it's also referred as just a GTPase. It has its active form that binds to the membrane of the cell. So we say that it has a slow diffusion because although it diffuses on the membrane, it doesn't diffuse as fast. And REC has also an inactive form that lives on the cytoplasm of the cell. Hence, it has a fast diffusion. This activation and inactivation happens often in the membrane, but is also autocatalyzed by the active. So whatever we have an active, whatever you have like a higher concentration of active REC, it tends to hold the concentration there because it self-promotes it. A good way to see what those solutions produce around the cell. We were talking about periodic boundary conditions and all that stuff before. In here, I the only space that I'm caring about in this particular image here is the edge of the cell. So basically the cell membrane. And here we can see that there is more active rec on the front of the cell than on the back. And here's the periodic boundary domain, because the back is represented both by this tail in the left and the tail in the right. Another thing to point out is that the inactive rec somewhat looks uniform on the domain. We can see a little downwards in the front. That's because of the fast diffusion. Whenever inactive rec is being used up, it kind of decreases globally on the entire cell. This is we can go on just on conversations on the math on why this holds polarization, but for now, that will be sufficient. Um, I've done some cellular plots model in the past with this formalism. In particular, this video here on the left, I have implemented optogenetics as well. So there is like a light field, which is represented by the blue field there. And I'm solving on the edge of the cell. So it's there's a solver and there's a CPM. So the solver and the CPM in this particular one are not talking too much. The PDE gets solved somewhere else. It transfers to the CPM, and then the CPM responds to that with pertusion, with all these biases and all this energetic stuff that we've been doing. But the goal that I want to have with CompuCell, at least as a hackathon project, is to convert to the simple wave pinning, which is this one that I presented, onto something that we can talk with laminopods. I really like this computation here, especially this model here that Gilberto was showing us. And I was at least imagining a little project that we could, you know, figure out what would be the best ways to implement this. Only the laminopod is moving, so maybe that's the only thing that's going to respond to rec, how we could put the directionality, all those biases. I feel like that would be somewhat a good discussion and a good project. Although I have some ideas, I don't have all the answers. That's why I'm in seek of teammates for sure. And well, going through the template that we went here, the goals that I have here is to translate the wave pinning appropriately to the laminopodia, meaning that maybe we want the cytoplasm to just respond to the laminopodia. The equation is actually being solved over there. Many thoughts. Um, because of this difference, I want to analyze the shape difference. This is a limitation of my model. If I show back that video, you see that the shape of the cell is not really it's not really changing there. There are ways to change the shape, but because I don't have the separation of, oh, there's the laminopodia part versus the cytoplasma part, I feel like there's going to be really good analysis on how does that change the morphology of the cell. And compare cellular tracks to data. Again, I have so much data about how these cells should behave when you have optogenetics on them. Even the simplest ones, there are complex data that I'm pretty sure the wave pinning cannot solve. That's even part of my thesis. But the wave pinning can represent a lot of them, and I feel like it would be a nice little slide to compare, like how does our model compare to real data. In terms of feasibility, well, I feel like, the model, the math part is already done. There's no heavy math to be done there. It's really just implementation on CompuCell 3D. So I feel like it's very feasible. Um, and every time we get a result that we think it's interesting, there's a ways for us to compare with the lab data to kind of say like, oh, we're going somewhat in the right direction. This is looking like how real cells would look like. So I think that contributes to the feasibility. And the project plan is really just this segmentation, like what is the best implementation of in the CompuCell model? How does that change the morphology? Maybe we can adapt some parameters, see how that plays around on the cell. Maybe we can even think about adding tension. That's a really important part of inhibition of rec. We can implement now a CPM way to revert to the model instead of just model giving something to the CPM. We can actually do the other way around. There are many things we can discuss here in project plans. Honestly, I don't want to spend much time here. Um, Two resources that I would recommend if whoever is interested. There is the wave pinning paper. This is not the analysis paper. This is the formulation of it for the first time. So there is some math on it, but it's not heavy math. I would say it's good to like just get an idea and a flavor of what the wave pinning really does. And on the bottom there is the paper from which I'm getting the data of the real cells. The paper is tackling on existence of a local negative inhibitor for the rec. I will not focus on that part. I will just mainly focus on their graphs and how they have like these cell tracks and how optogenetics works around that. Um, and the last slide here, just again, I essentially put my skills. I'm a mathematician. I work in mathematical biology, so I know a lot of math, I know a lot of code, and I know particularly a lot of the biology about this system, but I'm not a biologist. So I don't know how to make decisions. I don't know how to make assumptions that would be like biologically correct or not. So, if you are really good with biology, but you're seeking your math half, I think it would be a good match here. Um, but that's basically the work in the presentation that I want to give it to you guys for now. And I think my email is also on the Google Drive. If you want to send me an email there, there's all my information and stuff there. Yeah. Cool.
Ahmed's
I'm just watching.
questions. That's- I think
I
that's a
put a
great
question
idea.
in the chat.
Go ahead.
So I would say that the PDE model advantage is that you don't need compartmental cell.
Mhm.
So I don't understand why would you combine both.
Honestly, I when I was playing around with the Laminopodia video yesterday, and again, very rudimentary video because you're just choosing the direction randomly. The morphology of the cell is highly different than the morphologies that I will get just implementing the PD around the edge of the cell because you have just portion of the cell doing the protrusion instead of having maybe an entire big area of the cell. Or even if you have like a small little part, even if I decrease, for example, the length of the active rec portion, I would just get a very thin cell if I'm just doing one compartment. I presume that if I do with multiple compartments, I'll get very different morphologists. And that's the part that I'm mainly interested on.
Did you try increasing the cell size a lot?
I try increase the cell size, and but then again, I'm new to CompuCell. What I do, I all this CPM work that I do is in Morpheus. So I
Uh-huh.
don't know if you would act different in CompuCell. Maybe it does. Maybe I should try that. But when I try to implement, even with a large cell, it would eventually just elongate to be like this very long strip that was
Mm,
not too nice. Yeah, because
okay.
it, it's basically saying, oh, only this part of the cell is protruding. It only protrudes over that side. So you can implement that with aspherity as well. I played around with aspherity,
Hmm.
making the cell a little bit more liquid-like. Never got an interesting result though. Never got an interesting result.
Okay.
And I just looking at the Laminopodia video with the simplistic model that we have, it already looks a lot more interesting than all the results that I
Okay.
was able to get.
I think I could help you make the non-compartmental cell work.
Mhm. That would be good.
So yeah,
That would be
I
good.
think it is possible.
Cool. I
There
think if you
there
can
are
make the
some magics.
non-compartmental, we just make that on the
Yeah.
Laminopodia and then make the rest gets dragged by that. Something like that.
Yeah, because the real interesting thing would be that the lamellipodium should emerge from your equations rather than
Hmm.
define this is the lamellipodium period and then just solve there. You know,
Hmm.
I think it would be more fascinating if it was like just one cell, but that's just
Hmm.
like my opinion. And I think it
Yeah.
can work. So I will try some tricks.
One thing that I was thinking of doing, because my model is very deterministic, the PD part, right? Not the CPM.
Uh-huh.
And what I was studying, but this was me doing finite elements. So I went off of CPMs for a little bit. I worked a little bit on Phoenix. And there was a
Mhm.
model that I was working from Elliott. It's not particularly the wave binning, but it's a model that it would have these areas of high activity, but they would change constantly. The front would always be the same, but the activity would kind of like fluctuate on that. That fluctuation creates pods because then you're protruding part of the cell, then part of the cell, then part of the cell, then part of the cell. But in my deterministic models, because it's just a front, you can move that front, but it's a singular front. That front protrudes outwards and usually just squeeze the cells, right? It just gets into a shape and it stays on that shape. It doesn't produce this like uh I call the pseudopods, but it's really laminopods, yeah.
Okay, so
It
a
would be,
final
but
question.
this all this stuff would be
Mhm.
like an interesting discussion on its own, I think.
Yeah,
Just to
final
show this stuff.
question of yes or no. Do you import the shape of the cell into your PDE solver?
Uh no, no,
So that there's room
no.
for
There.
improvement there.
Yeah. We
Okay,
can think about that. Yeah.
all
The
right.
only thing I do, as I mentioned, is tension, but I don't it doesn't depend on the geometry, it's a global variable, right?
Yeah.
How away you are from your perimeter or your area that you desired.
Right. Thank you.
No, thank you. Good discussions.
I mean, CompuCell doesn't have some of the features Morpheus has for the surface diffusion. Something that we started a long time ago that you should talk to Julio about. We did it and then we never published it. We never finished it. We didn't use quite the ones you were using, but we did a PIP2, PIP3 model. We modeled PIP2 and PIP3 as species that want to be on the membrane and that like to be with each other. Like PIP2 likes to be with PIP2, PIP3 likes to be with PIP3. PIP2 and PIP3 repel each other.
Yep. Yep.
So they form islands. And then you can have one of them secrete a molecule, a molecular species that basically represents actomyosin protrusion, and then it causes the membrane to protrude. The other one causes the membrane to retract.
Yeah.
And that can give you self-organizing, and you can get patches where the cell competes in different places. So that's a possible extension. It's not quite as
That would be
elegant
really
as what
cool.
you have, but that one I know we can do.
I would love to take a look at that. I'd love to take a look at that.
So when Julia shows how to do the subcell molecular species, that might be something to do.
I'll keep it in mind too as a
That
history.
one
Yeah.
we wrote that model down, I don't know, 15 years ago and never did anything with it. I'd love to see that one get turned into something.
Yeah, that would be super great. That would be super great. For
Okay.
sure.
Anybody else have ideas for hackathon projects they wanted to bring up now? No? Thank you so much, Jupiter. That was great. We will come back at in 2:45 for the breakout sessions. We want to screen share the breakout information again and also put the links in the chat for people to